Okay, guys, Assalamu alaikum. So I'm going to discuss with you this chapter 29, okay, which is basically two resistance theory, okay, two resistance theory. This is gas and liquid, right? So we have gas, this is gas, so this is called bulk, and this is the liquid. Bulk gas or bulk means there is like it is far or it is away from the liquid film, okay. So right now there is no resistance, so this is the bulk, okay. Bulk consideration you will have in term of pressure or in term of mole fraction, so that will be YAG, okay. And same we have liquid, bulk liquid. Now when they come close to the liquid, the gas come close to, so now here it will feel some resistance. So concentration or pressure, whatever, it will drop. And this is the interface, gas liquid interface. I, so PAI, CAI, it could be for gas, it could be YAI, what fraction of Y, XAI for the liquid, right? So we have different units. So PAG minus PAI, that's the driving force in the gas film. Gas film is like on micro scale level. So we will have a drop in the concentration. So what do you have here in the gas film? PAG, that is the bulk pressure, minus PAI, that is at interface. This is the driving force. So now if you want to write a flux equation, so flux, flux is mole per unit area per unit time. So we need a proportionality constant, right? So that will be the kg. This is small kg, okay? So kg, this is uh, which is mass transfer coefficient based on gas, okay? This is small kg. We have to be careful, okay? So kg, small kg is the mass transfer coefficient in gas, and PAG minus PAI, which is interface pressure. Now we can have in term of this is bulk, right? So bulk, if in term of we have mole fraction in the gas, and then we will have and the interface also most mole fraction. So in that case the driving force is YA gas is bulk minus YAI, right? So this is the driving force. If we want to write a flux equation in this form, what it will be? Na equal so YAI, then it is ky, small ky times this. So all in both cases we have flux, isn't it? Flux and flux. So accordingly this kg, okay, this kg unit will change, isn't it? This is kg times this. So flux equal kg times this is pressure, isn't it? So unit of kg will be unit of flux divided by pressure. This flux in terms of ky, this is a mole fraction, it is unitless, okay. This is unitless means ky, unit of ky will be same as unit of flux, okay. Similarly we will have cai minus cal. So this is the driving force, cai minus cal, and then we have kl, small kl equal flux, okay. So kg in gas, kl in liquid. So mass transfer coefficient based on liquid and based of based on gas. So CAI is the interface to the bulk. After this, we don't have any resistance. So bulk consumption remains the constant. So if you see, this is the equation we have. Okay, this kg PAG minus PAI. This is the difference, and in liquid we have CAI minus CAL. Okay, so this is based on the local mass transfer, like based on gas, based on liquid. Then we have overall mass transfer coefficient. Overall mass transfer coefficient, if you see, it is based on overall, like from gas to liquid. Okay, so we have this one. So suppose this is the interface, this is the gas film, gas film, and we have the liquid film, isn't it? Liquid. Okay, 1 minute. So this one we can. Okay, this is better. So what we had before local in gas. Now from gas to liquid. So what we have here, from gas to liquid, up to here, like this. Okay, so in this case the driving force is PAG, the bulk, minus, if we are trying to write in term of overall mass transfer coefficient in gas, so kg, this is kg. Okay, now PAG to this one, this is from the equilibrium we can get equivalent concentration with respect to the CAL, with respect to the bulk concentration so what is the equivalent or equilibrium concentration of Pa with respect to this, the CAL, the bulk concentration in liquid? That is the driving force. So total mass transfer, this is the driving force from PAG to PA star. Okay, PAG to PA star. So then this kg is overall mass transfer coefficient, okay, with respect to gas. So this is the flux. Okay, so similarly you will have for liquid as well. Uh, so see, this is overall mass transfer coefficient, PAG minus PA star, and equilibrium gas pressure corresponding to CAL. So this one we will get it from equilibrium. So we should have something like from equation, from the data. So Pa star is in equilibrium with CAAL. Okay. Similarly for the liquid, we'll have KL, then Ca star. Okay. Ca star is in equilibrium with PAG. Okay. From the equilibrium relation we can get, we know PAG. So equivalent corresponding to this PAG, what is the concentration, equilibrium concentration? So that's the driving force, overall driving force. So overall heat mass transfer coefficient with respect to liquid is KL times this. Okay. Similarly, now we can have overall in term of this liquid. So Kx. Okay. Kx will be what? Mole fraction, right? Mole fraction of Xa star equilibrium minus XAL. So this is Kx. Okay. So we should know how to use these different forms. Depending on what is given, we will use the right equation. Okay, guys, this is up to here is clear. Um, okay, let me go to the notes I have uploaded. This one I have uploaded for you. Okay, this is very good summary. Now we can see for the just kg overall mass transfer coefficient in gas PAG minus PAI. This is interface pressure. When it is in terms of y, then we have more fractions. Then we will use ky. Okay, ky yag minus yai. So the unit of ky will be same as flux. Why? Because mole fraction doesn't have any unit. Okay. Now, in terms of if it is concentration given in the gas, this is the bulk concentration, this is equilibrium concentration. Then your mass transfer coefficient changes to Kc. Okay, Kc. So now the unit of Kc will be what? Unit of Kc will be unit of flux divided by concentration. Okay, you have to be careful. So unit flux is mole per unit like meter cube per unit time, right? Time. Then concentration is mole per unit volume, isn't it? Volume. Okay. 1 minute. I have this one. Mole per unit area, right? So flux is meter square, not meter cube. Mole per unit area. So mole and mole will cancel. So meter cube and meter square. This is 1 meter. So it will be meter per second. Unit of Kc, meter per second. Okay. So somehow we should know if one of the form is given, then we should be able to calculate other. Okay. So and similarly in term of overall, this is PAG minus PA star. The PA star is in equilibrium with the CAL, bulk liquid concentration. Same if it is KY and so on. Okay. Now for the liquid also, as we discussed, the corresponding equation will be for this liquid will be like this. Okay, one important thing here: resistance in the gas phase and total resistance. Okay, guys. Uh, when it is resistance in gas, so we will use kg. Kg is the mass transfer coefficient in gas, and then capital Kg overall. So overall this is mass transfer coefficient. So inverse of this is resistance, right? Like for example, conduction resistance is 1 over Ka, right? Convection resistance is 1 over Ha. So mass transfer coefficient, inverse of this is mass transfer resistance. So resistance in gas phase 1 over kg, and then this is 1 over K capital. So percentage resistance, and this becomes this one. So this could be given, and you have to find one of them. Same in liquid. So resistance liquid. If you use liquid, then you would use in both KL. Okay, or if it is KX, it's fine. KX and then 1 over. Sorry, KX capital K, right? So resistance Basically what is happening, you have gas, you have gas, you have liquid. So depending on like where is the more resistance, mass transfer dominating in gas phase or liquid phase. Okay. Okay, now this is what this relation is also very important. Equilibrium relation, linear equilibrium relation. So this equation are true for linear equilibrium relation. When if it's graph, then if it is linear, or we have y equals mx, something like this, or pa equal mca. So this is linear. In that case, if you know mass transfer coefficient in gas, mass transfer coefficient is in liquid, and then m. This m is the Henry constant. So this will relate mass concentration in gas phase to the gas in liquid phase. The equilibrium. Okay, so this is equilibrium basically. Y star P A star. Okay, so that m, then you can use this. This equation should be given. So if you know gas and liquid, 1 hour gas kg and m over this, you can get it. Similarly here. So liquid mass transfer coefficient given, then gas is given, then overall mass transfer coefficient based on liquid KL can be calculated. Okay. Now see, I told you different type of Henry law or equilibrium relation. So YA equals H or M, whatever. This is same as M. M and H, they are the same. Okay. Or we can have in terms of pressure and mole fraction, or pressure and concentration. In all cases, unit of H, the M will change. Okay. And now one more thing. This one is important, guys. Please, if you know one of them, okay, ky. If you know kg, and then you want to know ky. So what will you do? You will multiply with the pressure. Why? Because of unit. Because of the unit. You can see flux equal, if it is kg, then pa minus pai, right? Pag minus pi. So this kg is basically flux divided by pressure. And in terms of ky, small ky, okay, it will be yag minus yai. So this ky is unitless, and this one is flux. Sorry, this ky is not unitless. It is same as flux, but this one is flux divided by pressure. So if you want to get ky, you need to multiply kg with pressure. Okay, and same kx, you need to multiply with the concentration for kc. Okay, kc, because flux in a in term of kc, it will be concentration, right? So ca bulk minus cai. Okay, so kc is what? Kc is flux divided by concentration, and kx is same as flux, so you need to multiply with concentration. So these are important any information to change one form of mass transfer coefficient to another form. Okay, so that's it for the concepts. Okay, I will make another video for the questions. Okay, we'll take break.